Hello and welcome. This is an introduction to behavior in gaming, and this is the last lecture in the game development course. We will look at briefly in a broad way on topic related how can we model gaming using behavior, and specifically we will look at how can we program NPCs, non-player characters in your games and agents, of course. The first technique is called finite state machines, and finite state machine is a very typical technique that is used in computer science long time, and it's very easy to program and debug, and there's a little of computational overhead to use it. Basically, finite state machine, we model one character at a time, and basically we specify the different states of the character, and the same time the transition from one state to another. So you define that in the machine itself, or in the finite state automata or finite state machine itself. Remember that finite state machine or automata has been used in animation in Unity, and it's under the animator object, which is based on finite state machine. So it is used as a background end for programming or for modeling animations, and at the same time how to move from one animation to another. Now, in this context, in this lecture, we're going to use it to model any kind of action and behavior in our agent, not only on animation. So let's look at the definition of finite state machine. Typically, any finite state machine has 6 components: set of states, which means what's different state an agent can be, either idle or jumping or dancing, and so on and so forth. Also, we'll have a finite alphabet or event, what kind of event that moves the agent from one state to another. And this is typically found in any programming, in any game, where you define it from the beginning as a game, a game designer. In addition to that, there is a starting state, typically idle, for any agent. In addition to that, a set of accepted final state, and this is sometimes we skip for the sake of moving from one state to another, because in game development, normally we keep moving from one state to another. If we reach the end state, that means the player is, or the agent is dead, and at that moment it has to be destroyed. And important thing is how can, or what are the transition in the game or in the state of the agent. And we mentioned that event happens, but we need to tie each state with event and what is the next state to be done. And you will see that in a table. Typically, we'll define that in tables. However, in many cases, we don't have to use that. So we're gonna look at code. How can we develop everything from scratch? And we're gonna use it as a framework to develop other scenarios. In the next lecture or recording, you will see how can we use whatever code we present here as a hands-on, how can we use it in Unity to program a certain scenario. So a typical finite state machine is the exam of some agent who is patrolling, looking for hunting a player. So the player is free to move by you, by as a main player. However, there is agents who are patrolling the gameplay, looking for the player to hunt. And you'll see that the game agent can be either patrolling, or if case he sees the player, he can start attacking the player. However, there are other resources, or let's say limited resources to the agent, in which in terms of ammunition, If he runs out of ammunition, he will stop attacking, moves to searching for ammunition, and so on and so forth. Now, as you can see, these transitions are basically events, and these are conditions that happens while the player is, or the agent is happening, or what the game is happening. The states here typically are similar, that contain some, for example, animation that's happening, some action that's happening, maybe more, some basic variables that are changing according to the current states of the agent here. So these can be developed using a finite state machine. This is one way. We will see a couple of ways, or three or two ways to do that. And as you can see, we can program the states of finite state machine by structure programming, where we have 3 steps if you want to enter a state. First, the enter method, what you want to do as initial things before you enter the state. And after that, update, what you want to do continuously while you are in the state. And finally, if it happens that you are going to leave the state for any reason, for example, here, distance becomes more than 20, you want to execute a certain code or a certain action before you leave the state. So this is typically similar to what you have seen in Unity, where while you are running a script for any game object, you will see that you start with awake, start, update, or fix update, update, and after that late update, and continuously repeating this kind of thing, this method inside the game object. And this is happening exactly the same here if you opt to. By the way, this is having a state, having each state with 3 methods. It's a modeling option by the programmer. So you can say, no, I don't want 3, I just want to have update. That's fine. Again, the idea here is to show you how can you develop code by yourself modeling the finite state machine. Now, if you look here, this is the model in UML, where we will have a state machine, and the state machine, at the same time, we have basic states that represent different state of game object. Remember, this is an abstract design, which means we want to program the framework in which we're gonna tailor it according to the different game objects or different gaming games that we are going to develop. So we'll start with this as a class state machine. A state machine has only one variable, base state, and the base state here has, of course, it belongs to a state machine, and it has a name, and it has enter, update, update physics, exit, and so on and so forth. To be honest, these methods are, again, up to you what exactly you want to have. In the code that we will have, I think we're having enter, exit, and update logic. Optionally, you can have update physics and so on and so forth. It's up to you. You will see that the state machine extend the mono behavior. And why do we have the state machine extend the mono behavior? Because each state must be run continuously the same way as we will have it in Unity. So if a game object has a state, it has to continuously call update until achieving the code that you are targeting. That's why in a state machine we have a current state and it has start, update. So these methods are the same as the mono behavior. So you don't have them if you don't need them. However, you will have one method here where you need to change the current state to another state. And as you can see, typically you are in only one state, and based on the event that you will have, you will use this method to switch from one state to another. And states are children or subclass of base state, as we will see. Again, this is a framework. This is a framework code, and you will see, for example, this is exact implementation of the code. You will see it's very simple. it doesn't have that much code. Why? Because you need to use this code later when you have a concrete game object, a concrete states for a specific game object. So here's the base state class in Unity. Notice it's in C#. It doesn't extend anything, but it belongs to a state machine, and the state machine is here. Let me hide it just for simplicity. So a base state has a name, for example, idle, jumping, and so on and so forth. We will have a constructor. We will set the name of the state and the state machine that this state belongs to. And we will have enter, update logic, update physics, exit, whatever you like to. Whatever method you would like to, you can have them. Typically, you might not use any of them. Mainly, you might need use to update logic only. If this game object or the state of this game object involve physics, you might to add update physics. Similarly, what we have seen in game development. In Unity, if you need update, you rewrite the update or add code there. If you don't use it, you don't just keep it empty or just remove it. The same thing, if a game object doesn't need physics, there's no need to say a fixed update, because fixed update is specific for physics, and so on and so forth. So here we add methods, but this method, you will override it based on your needs. But typically they are empty, as you can see here. Now, these states are created based on your, for example, on your game that you are trying to develop, and we'll have a toy example in a second. Now let's look at the state machine. The state machine is a mono behavior, which means you have to have a awake, start, late update, and maybe fix update, and so on and so forth. So start, where you can initialize the current state of the game object, and you'll see a state machine has only one variable, which is a base state. And this is similar to the linked list data structure. This is data structure that can be implemented in different way. But as you can see here, we are implementing it, as a matter of fact, like a tree, like a binary. It has a root, and after that, each root has some other thing where you knew. As a matter of fact, here is not a tree. It's just a state machine. It has only one variable, the current state. And you should know which state you can go based on the event that you have. Now, the start method for the mono behavior here for the state machine, you need to choose wisely what is the current state of the state machine. And typically in any game object, you know what is the starting point or starting, let's say, state of that object. Once you know it, you can enter it, which means you can say current state dot enter, because you see here any state here, any state here, it has enter, update. So if it happens that you added code here, it will execute at the beginning, because enter means what? What code you want to run if you enter the state. Okay. Now update, the same thing here, where you can update the logic, update logic here. You'll see it here also. Update logic. So here you implement what code you want to do while you are in the current state. Late update, it includes something related to physics. If you want to do that, I'm sorry, it should be fixed update, but for some reason you're using it for late update. Anyway, one important thing with this one, which is change state. And change state, we assume that this method will be called by switching from, this is the new state that you want to go, and the current state, this is the current state. So you want to change the current state to the new state. And to do that first, you need to exist the current state. That's why you say current state exit. After that, you assign the machine with the new state, and after that you call enter. And this way you move from one state to another. And notice that get initial state here is virtual, which means it's different from one game object to another. So you need to override it and decide it in your code. So if you have these two classes saved in a file as a script in your Unity, typically these two classes will be reused to implement different scenarios. And we will see how can we do that in a second and using a toy example. So this is just a framework, okay? So let's look at an example where, again, I put at the top here the UML that I just mentioned, okay? And here I will be describing a simple game where you have, let's say, a square or a circle, let's say a square, and I have a ground, okay? And let's start that with this square as a game object. It's a rigid body, and this ground, which is a rigid object with a static rigid body. I want to implement the following. I want to implement a state machine, okay, where the rigid body can be controlled and can be in different states. So the idea here, the state machine is here. So the rigid body or the square will be idle, okay? Now this idle will stay, this square will stay idle until you hit the left or right arrow where it starts what moving. And moving means moving the left or to the right, moving to the left or to the right based on the input. It will keep moving to the left and the right until, if there's no input, you go back to idle. That means how many states do we have? We have two states. The first state for this game object is idle, and the second one is moving. So to develop this scenario, this toy example is very simple. Using this framework, we're gonna assume first that the two classes here exist in your Unity, and we're gonna extend them as follow. So the first thing, we create the state machine. As you can see here, the state machine, it extends state machine, which is the core, the class that is mono behavior. And as you can see, in the state machine, we have awake, okay, and we have initial state. Also, we can have on collision, because state machine, this state machine that we are extending is also mono behavior. So we can have everything we want to add, okay? The thing here is that the initial state of this object is going to be idle state. And idle state, as you can see here, is type what? Idle. And we will see, we'll look at the idle state in the next slide. But as you can see, movement state machine for this game object, which is a square, is a typical script where we have different kind of things that we need. We might have a rigid body, we might have sprint renderer. It's very similar to the script that we write, but instead of extending the mono behavior, we extend the state machine. And the only thing that we need to specify in the state machine, what is the initial state, which is idle, okay? And in the awake, when we create the state machine, you will see that we create idle state and moving state, because currently we have two states. And these two states are coming, the definition of these two states, separate scripts and classes, will be in the next slide. Okay. Notice that nothing happening here. Or you could say, how can we control how can we move from idle to moving to idle? You will not find it here. You will find it in the idle and moving script, as we will see in the next slide. So here currently we are just setting up the object. We are setting up the initial state here, okay? And we are defining what are the different states that we have, as you can see here. So we have two states, idle state and moving state, and the definition of idle state will be here, as you can see. Now let's look again. So this is the state machine, or the moving state machine here, okay, that will be attached to this game object. So previously, if you want to attach a script to a game object, which is in this case this square, typically we drag the script there to the script. So instead of having, now we are having a script that extending a state machine, and the state machine is extending the mono behavior. So anything that is a child or a grandchild of mono behavior can be used as a script that controls the object or the game object. Now this is the setup for state machine. You will see the details of things, how does it work here. So you will see here an idle state that extend base state. You see here some states that extend base states, okay? And in the base state, what we will have is a constructor where we assign the name of the state and which state machine that this state belongs to. We know that there's a state machine here, movement state SM. Okay, so you'll see that I will when you create the idle, you pass this, which is a movement SM. So here you will set them up. Okay, and here you will have an access to the state machine as a variable. So why do we need a variable to the state machine? Because we need to use the method of changing states. We want to change states from time to time if something happens, and change state happens in the state machine itself. So that's why we need a reference inside the state to the state machine. In addition, that typically any state must belong to a state machine. So we need a reference to that. This is the constructor. Now look at the enter and update logic. It's very simple logic for the idle. Here we are talking about idle. So when you enter the state, you can set a certain kind of initial state, initial coloring, initial, for example, variable in specific to the state. Currently, horizontal input here, where we have a variable float horizontal input as 0, you set it again to 0. You set the color of the square to black, for example, or you can do anything you want. If you want to set an animation, you can set it here also. You can pass a controller here and have a controller game object and set it according and so on and so forth. Now in the update logic, this is the method that keeps be called. It's like the update that keeps called by the Unity. And this happens why? Because if you look here in the update, we are in the update method, which is this method is the method that keeps called by the Unity. We are calling update logic. So update logic inside the update, so it will be kept called. So this method, update logic, we are waiting for input from the user. And if it happens that he pushed the right arrow or left or right, we recognize that. And if it was enough, he will hold it enough amount of time, or the get access horizontal, we received it positive or negative, we can move the object to what? As you can see, state machine change state to a moving state. You see that? So at this moment, what we're gonna do is moving from idle to another state which is moving. So this is the way. So basically update logic, you will stay in this state as long as no input was pressed. Once you, so here Unity will keep calling this method, which means you're not, once you encountered some input, okay, and the input was hold, or the user hold the input long enough, you will see that the state of the square will be moving, state machine change state to a moving state. And moving state, as you can see here, once you enter, you do some setup. As you can see here, you will change the cube to, or the square to red, and after that you adjust it, you move it, as you can see. So here update physics, it will be called, and as you can see here, you're gonna move it in a certain velocity, because this will be called too. So update logic and update physics will be called by the Unity, because again, here's, as you can see here, this is the state machine mono behavior. You have update, which call update logic, and you have also late update that calls update physics. So these two methods are called continuously, and so this one will be responsible for moving the object in a certain velocity left or right according to the input. Okay, and this one, update logic, will keep tracking the input. If no input was encountered here, what will happen? You go back to idle, as you can see here, and you go back again to this state. And so you will jump between idle and moving. And as you can see, someone might say or argue that this is simple scenario, and we have to create 3 classes: idle, moving, and the state machine. That's correct. However, this is just a toy example. In the future, you can incorporate other state. For example, you might incorporate a jumping state for the cube. And once you have the jumping state, what you can do, you can have, you can adjust the code in a modular way. And I admit it might cause some kind of hassle in terms of coding, and you need to change more than a place to do it. So, but anyway, you need to add the jump. At the same time, you need to specify the transition, change state from idle to jump. And as you can see here, there's no transition from jump to moving, which makes sense. Whilst jumping, he cannot move left or right unless he come and hit the ground. And as you can see, this anytime you want to add a state to the game object, you can add a state and define the transition to that state. Okay. Okay. The second model to do behavior is what's called behavior tree. And similar to final state machine, behavior tree is a task switching structure in autonomous agent, like a robot, like a zombie, like any NPC in the game. And you will see that it is based on what? Based on a tree where you have different goals to achieve for the NPC. And these goals might be either 2 goals to achieve or 1 goal, optional goal if you have several goals to achieve, or several state to be in. So basically, this is we try to solve a problem in which we have different action to choose from, or maybe to combine. At the same time, it provides us with a switching between the one state to another, or one behavior to another. We'll look at the structure or the basics for this tree. Before that, we'll look at the advantage of behavior tree over finite state machine. So the advantage is in terms of modularity, you will see fewer dependency between components, and this is we will encounter it in when we have the hands-on, or we look a little bit in the code. You'll see that finite state machines, there is stronger dependency. That means the state machine or each state must know about the next state. So they must know each other, because if you have in state X and something happens, you should know state Y to go there. So each state must know about the next state to go or to be switched to. In behavior tree, no, you don't have to. As a matter of fact, all what you need to know is your current states, and the structure of behavior tree will switch from one state to another based on your design, based on your whether you are programming what's so-called a sequence or a condition. And we'll look that in a second. Another thing, built-in hierarchy structure model action in many levels of details. That means if you have a very complicated scenarios, you can use behavior tree in a very neat way. At the same time, you can add behavior and remove behavior in a matter of maybe adjusting the tree itself by adding additional branches or removing branches. To be honest, this is similar somehow to finite state machine, because both of them you can add state or add branches, and at the same time you can remove, do the same thing. A neater way of representing the behavior is a graphical representation. Tree is more appealing than finite state machine in terms of representation. Now, let's look how behavior tree, the basic of behavior tree, how to handle things. It can handle things in a sequence, fallback, and interruption. And we'll look at these 3 terms in a second, in which you will have like more flexibility of handling scenarios, more than the finite state machine. So it will give you more power in terms of modeling different behavior of NPC or agent. Let's look at reason for switching task. Now, the basic thing is that any game object will be in a task. He will be busy doing a certain task, and the task, while you are in a certain task, okay, you might, or let's say state, okay, you don't stay in that state unless something happens, some event happens. And this event that's happening can be not only true and false, it's a three condition or three value state. So one reason to switch a task from one state or one task to another task, okay, is that you are finished. You finished or you are successful in that task. So if you are successful in that task, for example, you are looking for a jewel and you found the jewel, so you are done. That means you have to go out to do or to apply another or to execute another task. Another reason to switch a task is failure. You are looking for energy and palette, but you couldn't find. Okay, that means you need to switch to another to find other kind of energy in your game. So this is another reason where you need to switch task or to switch behavior in your game. A third one is maybe neither success nor failure. You are still in your task looking for something, or you didn't encounter any, let's say, failure. However, a new thing happening, a new danger, for example, a new task or a new condition that happens that prevent you from doing the current task. For example, if you are patrolling and you run out of energy, that means you have to switch your task, or you interrupt the current task. Why? To do something else to stay alive. So these three things can be modeled in your behavior tree and can be easily found in any programming any game object. So for example, success space game in a spaceship game, if you catch a jewel, you are successful. Now you can look for another, or you can look for patrolling or do something else. If you fail to catch a jewel, maybe you might need to go to patrol and look for another jewel factory to find another jewel or to find another pallet. It could happen that you might encounter an asteroid and you try to avoid it in the middle of searching for a jewel or maybe patrolling. So this is something called interruption, to interrupt your regular behavior because there's a dangerous or some asteroid coming. Now, behavior tree is structured in a tree, as you can see. And you will see there's a parent node, as you can see here, and it has two simple question mark and arrow, right arrow. Question mark indicates or, you can read it as or, and the arrow, right arrow, means and you can tell from simple logic that or indicates that one of the nodes or children node, if one of them is true, you just the parent becomes true. And from and behavior here, so for example, this one question mark indicates that if one of these children, which are each sandwich, each apple, and the other one eat banana, so indicate eat banana, if one of them is true, you don't continue to the next one. You just interrupt your behavior and go back and you finish. So this indicates an or condition. So you are looking for one of several options to achieve. The arrow here indicate and, which means if you are successful or you are, let's say, if you open a banana, you must eat it. So both of them will be executed in your control. And as you can see here, there is something called a fallback, which is question mark or. So one of the children should be successful or true, so that you can stop and go back. There's no need to continue. That's why they call it fallback. The other one called sequence, which means it will stop at the first child that return failure or running. So if you are here and you couldn't open the banana, there's no need to continue. You go back to the top. One important thing about behavior tree is that it's a tree where you executed in depth first or breadth first, depending on these parent node, either sequences or fallback. And typically you execute this behavior tree continuously as if in the update method. So the game engine will be running this or execute for each update. We know that update method in Unity will be called every time frame. So we will run the this behavior tree. We run it everywhere every time we call the update. So it will be continuously evaluated, continuously evaluated. And as you can see, there are some kind of task that will be executed. And depending on this condition, depending on which one is successful, which is not successful, the task will be executed. And in a second, we will see an example. Okay, so let's look at this example. This example starts at the top with the root. So this tree, you can think of it as a tree that has a root with OR. Question mark indicate fallback. Again, fallback question mark, and arrow indicate sequence. So the fallback means if one of these activity is successful, there's no need to continue to the next one. So basically we are running this in update. So the update, when you run the update, the behavior tree will run, will execute, which means we will evaluate each task and we will see whether it returns true or false. Okay, so this is a simple example we will see here. So question mark, which means I am hungry, I'm looking for to eat something. So if this is called in the update, he will start, of course, the behavior tree question mark, which means he will start to the left, to the first option, which is eat a sandwich. So eat a sandwich indicate that look for a sandwich. Okay, if you find a sandwich, eat it. Now you'll see here, if you are successful in eating a sandwich, you are done. There's no need to come here or here. Okay. However, if you are not successful, okay, so this depends on, let's say, the current situation in the game. If you are not successful, now you can go and try to find an apple and eat it. If you are successful, you're done and you are fine. Otherwise, if none of these found, you can go to a banana, and once if you find a banana, you can open the banana and eat it. Now here you have to do both, open and eat, because you cannot eat the banana without opening it. What if you don't find a banana? You will go here and you will end up with failure. And at the end, this execution of the behavior tree will be repeated in the next update. So one execution of the update, one execution of the behavior tree in the update is maybe it will stop here or here or here or none. It will do none because the situation is not working. So let's look at the run. So let's assume that you are running an update. So you start, you evaluate the first condition. This is OR. So that means you need to go down and evaluate this one. Find a sandwich and eat it. Here's red means failure. So if you couldn't find the sandwich, you have other options. Find an apple, and if you couldn't find the apple, you have a third option. So let's say that you found a banana. So you go, since there is a sequence here, you must, in addition to opening a banana, eat it, and you will end up all the way up with running, which means you are successful in the task of opening a banana. But this doesn't happen all the time, by the way. You could, for example, find a sandwich. You couldn't find a sandwich, find the apple, but you found an apple and you're done. There's no need to find a banana. Now, who decide this? You as a designer. So this is one goal or single goal achievement using OR. So you decide that among different scenario or tasks, I want to achieve one of several, and one of several is enough. Okay, so this might be, for example, find ammunition, and you have different kind of ammunition. Once you find one of the ammunition, you are satisfied, you returned and that one. So you could have, for example, here a question mark, find, let's say, bullets, find X, for example, find arrows, and so on and so forth. However, you can decide whether you want all of them or one of them by specifying whether you want a fallback or a sequence, as you can see here. Interruption. Sometimes while you are doing things, you can program things as interruption. And interruption indicates that while you are in the middle of something, you are checking something else. You need to avoid a certain danger. So here you'll see, as you can see here, we have a sequence, which means this must be true and this must be successful, and successful to stay alive, which means you want to avoid danger. At the same time, you want to eat. Okay, so you need to achieve both of them because this is a sequence, which means and. You want to achieve both of them to avoid danger and not starving. So these two goals condition, you can program it with arrow, as you can see here. Now this is modeled with, again, you will call this behavior tree in the update. So every time it evaluate both. So one time if you execute this in the update, you will start here and see no dangerous. If no dangerous or no alarm, everything is cool. That means this is true. And if this is true, you are successful because this is OR. So you will go back. So green, which is true, no dangerous. So there's no need to run away. You just go and look for eating to eat a banana. So here you will find the sandwich, you ate it, you are cool, you're done. Okay. Again, here we are trying to achieve two goals. At the same time, you want to avoid danger and you want to eat at the same time. Okay. Notice that which has based on this model, the priority is to avoid danger, because if we encounter a danger, we might die. So eating comes next. That's why we are trying to check dangers first. If there's no dangers, we go and look for eating. Here's another example. Let's say here we encounter no dangers, we go and we can try to find the sound we couldn't find. We tried to find the apple, we found, and all of a sudden, while we are eating an apple, alarm came. And when alarm came, what will happen here? You should leave the eating, right? Because some danger is coming, and what you're gonna go, because this becomes false, which means you have to run away. So stop eating and run away. This is called interruption, and interruption execute all the time. It's like as if a condition that must be checked all the time, even, which means if it was no dangers at the beginning, you must keep checking if a danger happens while you are what? Eating an apple. So if I scroll back a little bit, notice here, you can stay eating the apple for a while, right? Because this is executing update. So eventually at certain point while you are eating apple in this task, you could encounter something happens in which you encounter or you see a danger. And this danger automatically, for the agent, of course, if it happens that you encounter an alarm or a danger, automatically you go and you exit run away. So that means you exit the eating and you what? You go for running away to avoid being, for example, killed or danger. As you can see, you can program the behavior tree by adding additional tasks. For example, if you have more options to eat, you can add them, as you can see here. Also, not, for example, eating fries, for example, you can eat sandwich, fries, apple, you name it, depends on the game. Also, you can add additional activity in each branch. So for example, while you are eating a banana, you can eat the banana different way. You can break the banana or you can cut it, and after that you eat it. So you can add different tasks based on your just adding question mark. Why? Because this is either you break the banana or you cut it with a knife, and after that you eat it, because this is a sequencing. So you can model it in a neat way. As a matter of fact, you can have different structure with the banana, with behavior tree. Let's look at an example here about single goal achievement. So let's assume you want to go home, or an agent want to go home, and while he's going home, typically he want to open the door and enter. Now, if we can model this is a single goal. I want to enter a house, or my house. So a typical one is check the door. If the door is open, just enter and you're done. If the door is open, just enter, open the door and enter, you're done. What if the door is not open? You need to look for different tasks to achieve entering the house. And this can happen, for example, by looking for a key. Check the key if it's under for example, the mat or something. If you have a key, you open the door and you enter, you're done. What if you don't have a key? You can go and check the key with another person if he has access to the house. Or you might go and has a crowbar and something where you can break into the house, where you have, if you have a crowbar to lock on the door, and the door is thin, that means you can break it and enter. What if you are not successful in any of these? This becomes false and you can not enter. So as you can see, you can model different scenario with this. Here's another. So this is one goal scenario, one goal condition. And as you can see, you put or here, or a fallback. If you achieve one, you were done. If you don't achieve one, you go to the next, to the next, to the next, and you keep trying. You keep trying. Notice that this is called in the update, which means the execution will happen every time every time frame. Okay, maybe you will encounter, say, a certain kind of, let's say, energy or warmth. If you exhaust the warmth, you will die and the game will be over. But you keep checking the 3 or 4 branches of the tree here until you are successful. Once you are successful, you will be in the house, in the room, and you will be moving to another task or activity. Let's look at another scenario where you try to achieve 2 goal conditions. You want to be not freezing and at the same time not hungry. So not freezing, you want to get inside the house, and not hungry, you want to eat. So you need to achieve both. That's why you put what sequence, which means and this and this. And as you can see, if you are typically you are outside the house, so you need to achieve first not freezing. And typically, based on this scenario, the food is inside the house. So first you need to get in the house. Once you achieve that, you go and eat. Okay. Now, if you are not freezing, okay, that's fine. That means you don't need to achieve anything. As a matter of fact, you are fine. But if you are freezing, you need to come here, okay, and you need to look for a way to you need to get, of course, not freezing here. You come here and you check. If you are not freezing, you're fine. True. You go back here and you are like the sun is shining or something. But if this condition is false, that means you need, this is OR, that means you need to check this one and see if we can find something to get warm. For example, find a jacket. Okay. Now, if this is true, you're fine, you come and you are not freezing. However, if this is false, maybe you need to get inside the house and to get warm. And here you need to check the door open or not. Okay, to go inside. As you can see here, you can model different scenario for not freezing and different scenario for not starving or not being hungry. And as you can see here, here you have different things to eat, and here a different way to get warm in the behavior tree. As you can see, behavior tree can model complicated scenarios, and you can, as you can see here, you can combine them in a simple way, in a hierarchical way to build different models. As you can see here, condition is a strict way to model the scenario in behavior tree, and you can make it simpler, and you can also go in a more detailed behavior, as you can see here. Here's an example of behavior tree of Bachman, and this behavior tree of Bachman, basically he is we assume that Bachman is autonomous, so he's playing by itself, and he is achieving one goal in which he either eats a pallet, he is a pills so that he becomes stronger, or he is chasing or get chased by the ghost. And as you can see, goal one is eat a pallet. The other goal is avoid chase ghost. And this is or this is fall back, in which you'll see that the tree evaluate and you'll do the rest. Now, I'm not gonna go over the coding part. Again, in the slide, you'll see some code, how to represent each node in the tree, and some methods to set up the information that you might need to add in each. So basically, to model any kind of things, you need to model a node. And of course, there's a three kind of node. A task node where you need to have some action, a node that is a fallback or, and a node that is a sequence where you have to do everything below. And as you from here, you can see that you can do different kind of recursion part in this. As you can see, you can look at the code and make sense of it. Basically, it's a very simple code where you have a behavior tree extend mono behavior, and basically in the update we are calling, or you are evaluating the behavior tree in the update method. Now, the behavior tree has a node which is the root. However, the root might be big. As you can see, this is the root and has children. So basically, you build this tree based on your model, based on your what you want your agent to do. And once you do that, you'll see this is the node, and this is the basic or the parent node, the abstract node. It has a state. It has different kind of children. A node can have several children, as you can see, and it has evaluate too. You can evaluate the node. You can attach a child. You have evaluate, as you can see. You can attach children to this node, and you can save some data that you need while the node is working. Okay. There are two kinds of nodes in addition to the parent node, which is a task node. You can have a sequence node, which is this one, where you have to do three things or more than, which is ANDing, because you have to implement this one and this one and this one all together. And as you can see, you are successful if all of them are successful. If one of them failed, that means you failed, you retain F. And there's another case where it's running, which means you're still turning away or still running away, you're still running. And this one is also 3. So look at this code if you are interested in. I'm not expecting you to understand fully, because we're not gonna look at that in this semester at least. In the future, we might look more on how to develop this. However, I will be it's important to understand how behavior tree is working, and remember that the evaluation of behavior tree happening every update in the update method, which means every time frame. Here's the code, look at it. Okay, so here's the example of as you can see, toy example. Use previous framework to model the below scenario. A player, or not a player, he is the agent is patrolling the gameplay. If an enemy is spotted, the player interrupts its patrolling and moves toward the enemy to, let's say, to hunt him. If the enemy is in attack range, the player attacks. Okay, so as you can see here, here's the, so this is a one goal scenario where he is either attacking or he is patrolling. Okay, so as you can see here, we have three scenarios. Either you are in a normal situation patrolling, but more important than patrolling is you want to avoid or attack the enemy to collect certain kind of thing. So that's why we put it in the left hand side, because we know by default the behavior tree executes from left to right. If one of them is successful, you stop and go back, because this is OR, as you can see. So this is how to design these scenarios. You start with what is your priority task? Is it patrolling, or to avoid or check enemy and maybe avoid enemy or attack the enemy? So the first thing is check enemy in range. If it's true, go ahead and attack. If this is not true, you go back and check for the range or for a target. Look for a target. If none of them correct or none of them successful, you stay patrolling as normal. And this is happening in many agents where you are typically patrolling at any moment. At any moment while you are, the update is calling every time frame, or this behavior tree is running every time frame. If you, while you are patrolling, something happens in which you check the enemy in range, you find it in range, you switch from patrolling to this part where you attacking a task of the enemy. If this is not correct or not successful, you start looking for a target while you are patrolling, and so on and so forth. Here's how to set up the example, how to do attack tree of that extend behavior tree and do the rest of the code. Again, look at that if you are interested. Okay. Please drop me any question regarding this. By now I am done with this presentation. Maybe I will have two kind of things next class. I will have one hands-on and one related to the remaining of this task or remaining of this lecture about other way of AI in gaming. And if you have question, prepare a question through the email, or prepare or send me a question during the next lecture. Thank you very much, and see you next time.